Here's another Born-Haber example, this time with magnesium oxide. First of all, it says which ions are present in magnesium oxide, and the answer is Mg2+ and O2- because magnesium is in group 2 and oxygen is in group 6. So the question may ask, calculate the enthalpy change for the reaction magnesium reacting with oxygen to give you magnesium oxide. And then it also says as a supplementary question, what kind of enthalpy change is this? And this is the standard enthalpy of formation of magnesium oxide, because you're starting from the elements and you're ending up with the compound. So the data which would be given in the question would be the atomization energy of oxygen, the energy required to get oxygen molecules into oxygen atoms, atomization energy of magnesium to go from magnesium as a solid to magnesium gas, first ionization energy of magnesium, and that is stripping an electron off magnesium atoms, the second ionization energy of magnesium, that's stripping a second electron off the Mg+ ions, first electron affinity of oxygen, adding an electron to oxygen, second electron affinity of oxygen, adding a second electron to oxygen, and then the lattice energy of the magnesium oxide. So drawing a Born-Haber cycle and putting on the data gives this diagram. Here we have magnesium in the solid phase. We want to atomize to get it to magnesium in the gas phase. Then we want to ionize twice to get it to magnesium 2+. Here's oxygen as a molecule. We want to atomize to make it oxygen atoms. Then we want to add electrons. That's the first electron affinity and the second electron affinity to make oxide ions O2-. And we can also add the lattice energy as well. To work out delta H, it's a matter of going up this arrows and down this arrow here. So plus 148 plus 1451 and the 738 gets you from magnesium solid to magnesium 2+ in the gas phase. This bracket here is the oxygen starting from the molecule 249798 and the -141 to get you to O2- gas, and the -3791 is the lattice energy. Calculation continues, so there's the magnesium side, this is the oxygen side, this is the lattice energy side, gives you overall a negative enthalpy change as you'd expect. Worth noting that the actual value for this reaction is slightly more exothermic, -602 kilojoules per mole, and this is because there is a degree of covalent character in magnesium oxide, and therefore the bonds formed are slightly stronger than those predicted by a purely ionic model, and Born-Haber is a purely ionic model.